Hi, everybody. I'm Sébastien Deleuze. I'm working as a Spring Framework committer at VMware. I have led the introduction of GraalVM native and Kotlin in the Spring ecosystem. And today, with Moritz, we are talking about going from the experimental Spring Native project to Spring Boot 3 native support, basically.
Yeah, thanks, Sebastian. So my name is Moritz Halbritter. I work since February 2022 in the Spring Boot team, so you may not know me yet. So I hope you attended the keynote because Alina Jurenko explained to us why we want to compile to native. I'm going to show essentially the same slide, but I'm going a little bit more in depth into the technical details. So the first thing you will notice if you are compiling your application into a native image is that this has an instant startup. So instead of using 1 second, for example, or 10 seconds to start up, this starts really, really fast, like 2 digits milliseconds. And that's because it's all compiled ahead of time. So all the AOT stuff is ahead of time compilation. So it's compiled while you're building it and not while you're running it. So you don't need to let the JIT compiler kick in, compile your classes, load all the JVM, load all the classes. This is all already done. Which hooks into the next point, which is you don't have a warm-up phase. So you essentially get peak performance immediately because it's all compiled. You don't need to call method 10,000 times to get the profiling compiler kick in, let it profile, then compile it into native machine code, then optimize it, maybe de-optimize it. It's all compiled ahead of time. What you also get is low resource usage because you essentially don't pay the overhead for the JVM. So the JVM does a lot of stuff, tracking method invocations, running profilers, running JIT compilers. All that stuff is gone. You don't have it anymore. And the garbage collector from the native image, if you're using the community edition, you essentially get the serial garbage collector, which has even less overhead than normally the G1. You can also use the G1, but you need the enterprise edition for that. You also get reduced attack surface, which is quite surprising. How this stuff is working in the native image is you point it at your main class, and then it starts looking for reachable code from starting from the main class. This is the tree shaking algorithm you may be knowing from front end. So essentially, it takes all the stuff which it can reach, then it shakes it, and all the stuff which falls down, it just removes. Okay? So there is less stuff which attackers can exploit in your application. Plus, you need to explicitly enable reflection and serialization access. So all the stuff which you have not enabled reflection for, you can't execute via some log4j attacks or something like this. And what you also get is because everything is smaller, you don't need a JVM anymore. You can compile it all to a native executable. You could even compile it statically, so you don't need any libcs for that. You can essentially run it on a distro-less container image, and your container image is then the same size as your application, which is like maybe 50 megs or something.
Yeah, so let's have a deeper look on the various use cases, because you may wonder, when is it a good idea to use native image? Where is it a good idea to keep using the JVM? So first, it depends on your context, so no easy answer. But typically, the use cases where native images are recommended are if you are running on very small and cheap cloud instances, low memory, low CPU. The JVM is not really designed to work on a machine with 1 CPU. So yeah, it could be a good use case. If you want to scale to 0, I presented that topic in the keynote quite a lot. If you want to use function as a service, then native images with instant startup and peak performance available immediately are a pretty good fit. If you are using microservices architecture, if you are creating back offices, if you are deploying on Kubernetes platforms, if you are deploying your software as a container image, you should assess if that's a good case. That could be the case. If you are using agent-based observability, so some agent-based observability begin to support native image by allowing to use the agent to augment the bytecode at build time, so it depends. So check with your observability provider. There is a beginning of agent support for native, so depends. And if you have a lot of memory, a lot of CPU, if you are doing very frequent deployments, a very long build time with native may be a drawback. If you have a high traffic website, maybe the JVM is just a better fit. If you are using unsupported dependencies, big monolithic applications, so yeah, maybe here GraalVM is a better fit, but up to you to check with your use case. So yeah, a bit of history. So I think 2 years ago, we announced Spring Native, times fly. So Spring Native was this experimental project where we basically tried a lot of things. I think we rewrote the ahead of time engine 3 times, trying various approaches, getting a lot of feedback from the community. So thanks for everybody for providing a lot of inputs. That really helped to shape a good support in Spring Boot 3. So here, yeah, Spring Boot 3 really introduces official support for compiling application to native executable. It totally supersedes Spring Native, so Spring Native is now archived. We don't support it anymore. And on every metrics, every level of quality, documentation, Spring Boot 3 native support is just better. So just use Spring Boot 3. That means you need to switch to Java 17. You need to switch to Jakarta EE, but yeah, that's really the way to go.
Okay, say we now got you on the native image track and you want to try it, and we have a demo prepared how to get started, and I hope you can see it in the background. So first we open up the Spring initializer. Then we are going to take at least the version 3. We clicked on the GraalVM native support, and then I added the web, and then generated it and opened it in my IDE. And what you can see there, this is the Grail build file. What's new in there is the plugin there, the native build tools from the GraalVM team, and no other dependencies, so no Spring Native dependency anymore. It's all baked into Framework, Boot, and all the portfolio projects. If you take a look at the help file, you'll see that there is quite some documentation about the GraalVM native image, and this is actually sped up where I scroll through that stuff. So there's a lot of reading if you're interested, how the stuff working under the hood, what are the caveats, what are best practices and stuff like this. So there's a lot to read. You also see how to build that stuff with either the build packs or with the native build plugin. I'm going to talk about it later. So let's take a little bit about the code. So what I did, I created a controller, a logger. The logger just gets a parameter from the request, and it returns it, and it defaults to Spring IO. Okay, so we are going to run that one on the JVM first, and what I do is I use SDKman to use the native image kit from Liberica, which is a GraalVM distribution, but you can also use the original one from the GraalVM. And then you get the native image tool, which compiles your jar into your native image. And then you can type GraalW boot run, and now it's running on the JVM, okay? So just to show you that this code there I wrote, it's working. So I execute it with my name, I get back hello Moritz, okay? Great, if I leave it out, I get the default Spring IO. Okay, so no surprise yet. Let's take a look what happens if it compiled to native. And I've sped it up 3 times because it's take 1 minute, and I don't want to stand 1 minute here and wait for Grail to do. So what the native image is doing, it's analyzing your application, finds all the code which needs to be included there. It also downloads some JSON files which enable reflection. I'm going to talk about it later. And then 1 minute later, I get a native image. And if you take a look what it is, it's 65 megabyte of a native image. And this is all you need to run it. You don't need any JVM anymore. It just runs. And you see it starts in like 52 milliseconds, which is very nice. And to demonstrate that it's still working, I execute it, you get back Spring IO, and you got back hello Moritz. And you see it logs, so I've not faked that stuff. Take a look at tests, because tests also work. I did an integration test, I auto-wired the test REST template, I executed against the controller and asserted. And now I run GraalW native test, and what this does, it now compiles my application with a JUnit runner, with JUnit in it, and then it executes those tests inside the native image. And there you see there is process AUT stuff going on, and it's printing banners. What is happening? I'm going to talk about that later in depth. So now it's sped up too, because it's compiling all the application plus more, so it takes like 1 minute. And then you see that it executes your unit tests inside the native image, okay? And there you can see the test, which I wrote there. It executed successful, so it found 1 test, it started 1 test, and 1 test was successful, so yay. And that's essentially how you can run your application in a native image, and you also get native testing support, which is great, because if your unit tests pass in a native image, you get more confidence that this stuff really runs in your production systems. So we baselined on GraalVM 22.3. The GraalVM version support policy is that we now using 22.3, but there is an upcoming GraalVM release which is 23.0, and we are also going to support that. So what's in that update is there is better performance, less memory consumption and stuff like this, compatibility improvements, also the bundle stuff where you can build your native image into a bundle and then use it for reproducible builds or build it somewhere else. And there is also experimental JMX support, so for JMX exported metrics. We also have the Spring Runtime, which is the commercial offering from VMware if you need support for that, and we extended that to also cover the native stuff. So if you encounter problems with the native stuff, you could go to VMware, and then we were able to help you. The thing you saw, the SDK use native image kit thingy, is from Belsoft. Belsoft is the partner where we're partnering with for the JVM support, and they also have a GraalVM installation which is called NIK, the native image kit. This is essentially the GraalVM compiler containing the native image. If you need help and we actually find a bug in GraalVM, that stuff is not incorporated in some closed source stuff, so it's all contributed upstream, so we are honoring the open source. So say now your application is working, but you maybe use a library which we hadn't in mind when designing all that stuff. So how does that work? So there is the GraalVM reachability metadata repository, and if you take a look at this is on GitHub on the GraalVM space. It's a lot of JSON files, and those JSON files essentially make libraries which are not native compatible out of the box compatible. Okay, so there are some stuff which does not work in native image. So for example, we have reflection which must be enabled. We have serialization, we have proxy generation, we have JNI calls, and we have resource loading. And all that stuff needs special hints for various reasons. And if the library can incorporate those hints on their own code base, but if they are not be able or not be willing to do that, there's this GraalVM reachability metadata, where we essentially, or the community, wrote a lot of JSON files which make then not compatible libraries compatible, and there is a lot of stuff going on. So for example, you can see a logback in there, you can see the DataStax driver for Cassandra, I think it is. There you see Consul APIs, you see the Hikari connection pool which Spring Boot is using by default. And this was initially a GraalVM and Spring-driven support effort, so we started that thingy, but now it's open for public contribution, and we got stuff from the Macronaut team, for example. There are also guidelines how to craft that configuration. So say you find your library which does not have any GraalVM support and you want to make it compatible, you go to that repository, there's a contributing guide, it tells you how to set up those tests, so essentially using the native test facility I just shown to run integration tests. Then you need to take special care about, for example, runtime initialization. Sébastien is going to talk about that soon. So we don't use build-time initialization. You have reachability-based native configurations, which are complicated words for you get a smaller image. And we have mandatory native testing. So it's not only JSON, it is also test code, which makes sure that this JSON stuff works with the library. Okay, so we get failing tests if we upgrade that library and the JSON file does not match. So that is stuff does not blow up in your production systems, but blow up in the CI pipeline.
Okay, so maybe a deeper look of some things under the hood. On Spring Native, and generally when you begin to support native images, there is some code paths that are not really compatible with native, so you may want to take some shortcut and basically override some methods by some native compliant methods. So this is possible thanks to GraalVM substitutions. We have used that a lot in Spring Native originally. And a big part of the work we did for Spring Boot 3 native support to call it production ready is to basically remove any substitution. Why would you want to do that? Because imagine you have a CVE that is fixed on a method in your upstream library. You are overriding it for native compatibility. Basically, you are just removing the CVE fix and you are under yeah, you have issues there. So it's also maintainability issues, because what if the upstream library is fixing a bug and you are still providing your old native compliant code path with the bug? That's a nightmare. And it's also a debuggability issue, because if you are debugging the code on the GVM, the code that will execute on native will not be the same, and so here troubles begin. So it's maybe not super visible, but in practice, in Spring Boot 3 native support, we have 0 library substitution. We have worked on that for 3 years. It has been painful, difficult. Thanks for the GraalVM team. Thanks, Alina, for the GraalVM team for fixing a lot of bugs, because in order to remove substitution on Spring side, a lot of bugs needed to be fixed on GraalVM side. Some adaptation needed to be done on upstream libraries. And so this is not super visible, but I think this is super important to make sure that your code you run in production in your native image is the code of your open source libraries. Another under the hood concern is that, so I think when GraalVM native image was created, build time initialization was the default. Just before going GA, there was a switch to go back to runtime initialization. So that may sound a bit strange, but basically, build time versus runtime does not change a lot of things with native image for the startup time. It's mainly an optimization that allows to have smaller footprints. So that's tempting to initialize a lot of things at build time. But by design, build time initialization of a class, so the static field, the static methods, static field mainly, are incompatible with the runtime initialization, which is the default behavior on the GVM. So if you have a class that is initialized at build time, all the class transitively used need be also initialized at build time. And the end result, and we had that with the logging libraries, you have, by design, unsolvable issues, because you have a part of your code that need to be initialized at runtime, the other part at build time, and you are totally blocked.
Let's say you have a class and there is a static logger field, and this stuff is build time initialized. What is happening? It's essentially initializing all the logging system. It starts reading your logging configuration files, and then you're stuck at runtime because you can't change log levels anymore for that class.
Yeah, so build time initialization is okay if that's an automatic optimization done by GraalVM without any side effect. So in practice with GraalVM, there is some build time initialization, but it is the job of the GraalVM native image compiler to do it automatically based on the analysis that there is no side effect, and this is perfectly fine. Where we say there is no explicit build time initialization is on Spring side. We don't have any ins to say this class is initialized at build time. By default, same behavior than on the GVM, runtime initialization, and the startup time is great. And we have collaborated with the GraalVM team to optimize the footprint, to remove some code at build time without to do this kind of thing. And the end result is that we have removed a lot of compatibility issues, and that there is still a few places where build time init is required by GraalVM, but that will evolve and be fixed. So another thing that is really important. We are providing a runtime ints API that we are going to demonstrate. Basically, a nice friend API to add ints without having to basically do a mistake in your JSON, forgetting a comma or whatever. And I think that's useful. So let's see that in a demo. So here we are going to port the famous pet clinic. Okay. Great. Not sure why. We are going to port the pet clinic to, let's start.
Try pressing F.
Yeah.
Okay.
Let's start from the beginning. Okay, so we have our famous pet clinic application, and we are going to add native support to it. So what we do here is that we are adding the native build tools plugin, so native Maven plugin. There is also a Gradle one. It will be automatically recognized by Spring Boot. Spring Boot also manages the version by default, and that will enable you to do your native build. Then you need to declare a few specific stuff that are really specific to your application. So here we have a messages resource bundle that we want to declare. A lot of other files are automatically included by Spring Boot because this is well-known files. This messages resource bundle is specific to our application, and GraalVM requires to be a bit more explicit. So you can see that with the runtime ints API, we can specify resources, reflection, serialization, etc. Here we are just going to register messages resource bundle. You could declare also reflection for any classes with fine-grained control, etc. And we are going to use @import runtime ints in order to make this class used in practice. Then typically you may use reflection based serialization or sometimes templating system like TeamLeaf or Mustache that will require additional hints because the type is not exposed on the public API of the controller. So for those use cases, we have the @register reflection for binding, which basically add automatically the required reflection entries, including for the transitively used type for reflection, etc. Then we run a native build with Maven-p native compile. So same kind of native compilation that you demonstrated previously. Yeah, a little bit of fast forwarding because we don't want to wait too much. So this is on my fast gaming machine. So 1 minute, maybe 2 minutes on your machine. And we can start the pet clinic pretty fast with this native executable in just a few milliseconds. And this kind of times, you get the same on production, so it's not a few milliseconds on locally and on production that will be 3 seconds, that remain a few milliseconds in the cloud.
We got benchmarks later to show that it's stuff working on restricted machines and not only on this gaming machine.
So let's do the full screen dance. Okay.
So I promise we take a look under the covers how that stuff is really technically implemented. So this is essentially all the building blocks which are in there, which make all the magic work. So we have this stuff the GraalVM team provides. So we have the native image compiler, which takes your jar with the bytecode in it and compiles it into a native image, which is then executable right on your machine without a JDK. You have the native build tools. This is the thing Sébastien added in his demo, the Maven plugin, and there's also the Gradle plugin, which I used in my demo. This is the thing which you put into the plugins block from Gradle. This is the native build tools, and what it does is essentially it kickstarts a native image pointing on your classes, and then it compiles all that stuff. And there's the reachability metadata repository, which makes incompatible libraries compatible. And the native build tools actually looks at your dependencies and downloads all the correct versions for it and puts the JSON in the right place so everything is just working for you, so to provide a nice developer experience. Then there are the packetable build packs, and build packs, I'm going to talk about it later in detail, are essentially the idea that you don't need a GraalVM distribution on your machine, but you only need Docker, and then it pulls all the stuff it needs, and you only points it to the source files, and then it compiles it in the Docker, and then it builds a native image in the Docker, and it spits out another Docker image, which you can just run.
Yeah, without having to write your own Docker file, basically. Just package it in a nice way by default.
Yeah, you point it to the source code, and then it applies all the best practices, and then you get an optimized image, which you can just execute. So, and then there's the stuff which the whole Spring team did. So this was not an effort only on framework and on boot side, but all portfolio projects, like, data, security, all other cloud, they all did work for that, so it was a huge undertaking. It's based on the AOT transformation engine, which lives in the framework, and what it does, it essentially, so Spring uses traditionally a lot of reflection, for example, to do the dependency injection. It's all based on runtime, so it instructs, it sees what your constructors are, and then it looks up the dependencies, and then it puts those stuff in the constructor, and it's called reflectively. What the AOT transformation engine is essentially doing, it's eliminating this reflection stuff. So it writes code which does the dependency injection for you, and it does even more. There are hook points into the engines, which are the plugin interface, and then the portfolio projects, they have their own AOT transformations, for example, to do the magic behind the Spring Data interface repository things, where you can say find by name something, and then this stuff gets transformed into actual source code. And sometimes, if we can't eliminate all reflection hints, there are also some hints to make the reflection stuff working. And then Spring Boot comes and ties it all together. There is the AOT and native integration into the boot plugins. So the boot plugin got more clever. If it detects that you also have the NBT plugin, so the native build tools plugin, then it starts the transformation engine when you build the application, and wires it all together, so at the end it spits out a native executable. And there's also the native documentation which we wrote, where you can read screen pages after screen pages of all that stuff. Okay, so now we know the building blocks. How are they really working together. So normally your application looks like this. So there are your source files, which are then compiled by compiler plugins, and there are your resources, for example, the resource bundle, which Sébastien showed. Then the AOT magic kicks in. So we have the generate AOT sources and AOT classes, and this is another build step, okay? So it starts your application onto a certain point, and then it looks at all that stuff. We're going to see that in a demo later. When the AOT is then done, your application consists of your compiled sources, and we have not touched that stuff, okay? So we don't fiddle with your code, because we want, if that stuff blows up, it's your fault and not our fault. It's also your resources, we didn't touch it. There are now the compiled AOT sources, which this thing here has generated. It gets compiled and put into there. And sometimes there are also classes which have no source code equivalent. So for example, if you use cglib proxies are generated at runtime, and they are only existing with bytecode. And what we are doing is we are capturing this bytecode, write it to disk, and then put it inside the jar. And if it then runs if you start it again, it uses the captured image of the proxy, essentially. And there's also native image config, which, for example, we generated for your return types of controller methods. So to enable JSON serialization, XML serialization, and stuff like this. So our idea is that you don't have to provide hints for yourself if we can find them out. So if you put it in a public, in an API, which we can introspect, like if you return it from a controller, we see, okay, this type is returned from a controller. Maybe we should register reflection hints for that so that Jackson is working on it. And then you have two ways to run that stuff. You either run native compile, so the native build tools plugin kicks in, it runs native image on all that stuff, and then you get a native binary which you can then execute. Or you could also run the boot jar, and then the boot jar contains not only this stuff, but only this stuff. And then you can decide at runtime if you want to use the new code path or the old reflection-based, essentially. And there are small performance benefits for it. We have some figures later. So let's take a look how that works. And we are going to take a look at the tons of JSON in there. Okay, so this is a small application project. It's as a Spring Boot application, like you know it. We have an interface, which just has one method. And there is a controller. It uses this service, which I just shown, dependency injected into the controller. If you run the controller, it calls the service. There's the implementation of the service, annotated with the edge service, implementing this interface. And if you run the hello method, it uses a greeting. It reads from the config and returns you and prepends your name. Here you see it's reading this application configuration from application.myService from your application properties. Okay. Then let's just build it. And this is not building the native image, it's just running the compile stuff. And here you can see there's a Spring banner on it. Normally, this stuff only pops up when you run the application, and now it's running inside your build. So what this thing is doing, it's bootstrapping your application context to a certain point, finds out which beans are there, and then generates source code to restore those beans. And now we are going to take a look at those source code. So you can actually open that stuff up in your IDE. So first we are going to take a look at the native image properties. This is essentially the configuration for the native image. And this points back to your entry point. This is the entry point of your application. And this stuff here is the JSON we generated to make reflection work. And this is quite some stuff. And your, for example, return types of controller methods are in there too. This is to make your resources working. For example, you see that it reads the application properties from the class path, the application YAML if you're using the YAML support, and more stuff. For example, the logging configuration. Now let's take a look at the sources which are generated. So the most important thing is the application context initializer. The application context initializer is a thing from framework, and this thing is essentially doing what it says. It initializes your application context so that the application context is ready. And then we see there is generated code, so the __ stuff is our generated code. And if you take a look at it, it even has Java doc. Isn't that great? There you can see all the beans which the process AOT thing has found while bootstrapping your application, and then it generates code for it. And there you can see your own beans. There is the demo application, so the application main method, the default my service, and the controller. If we take a look at this, this is the controller definition. So the type is my controller. There is the root bean definition, which is the blueprint to tell Spring, if you want that bean, call the setInstance supplier, which is this method on the top. And here you can see it's just newing up the controller. And here is the dependency injection. And you see there is a new in there, okay? This is essentially, this argument here gets then passed to this controller. Okay, so where is this service coming from? So let's take a look at this code. There is another root bean definition for this one, type default my service. If you want a Spring, if you want an instance, call this. And here you can see another new call, which injects the properties. Okay? So now we have to chase it down. Where are the properties? And they are still in there. And you can take a, this is the main application method. And here you can see the package structure of your stuff is mirrored here. And here you can see here is the bean type of this configuration property. And here you can see we are just calling new. Okay? So all the reflection stuff for dependency injection is gone. It's all readable Java code if you want to read that stuff. And this is all tied together with this big method where it all registers all the beans, so the beans which are there by default or the beans which you provided. And here you can see there are a lot of dollar signs, Spring zglib, whatever. This is the captured zglib proxy, and you see this is decompiled bytecode, and this is essentially the captured zglib proxy which has been created at the, when you type Gradle you build, we capture the proxy, write it to disk. All the same thing is happening for your tests too, because they need to run in the native image. So now we can test it out. Okay, there is a jar file, and you can run it. Okay, and it starts in 800 milliseconds, but you can also enable Spring AOT enabled as a system property and set it to true, and then you can see it's starting in 800 milliseconds, it's starting in 600 something milliseconds, and it says starting AOT process. So now it's using the code path from all the code which I shown above. Okay, so this is working completely without native image. You can also run it on a regular JVM using all the AOT stuff.
Yeah, and we have recently added, that's a bit of a secret hidden feature of Spring Boot and Spring Framework. Recently you have added documentation.
Yeah.
If you go to my github.com/sdeleuze, there is a Spring JVM AOT samples and Spring AOT profiles where you can find concretely more samples to use it on the JVM. And it's useful for performance reasons, like I showed in the keynote, and also for debugging purpose. The code that runs on native is the AOT one, so if you want to debug exactly what happened on native, just use the AOT mode on the JVM, use the regular debugger. This is exactly what happened.
Yeah, just put a breakpoint in this generated code and you see.
Yeah. So, okay.
Okay. Another question we often get is, what about the profile stuff? We somewhere said the profiles are not supported, which was not the whole story. So profiles are supported, but they have a caveat. So what's up with our videos? Okay. So let's take a look at profiles. Okay, there is the service again, and now we have two implementations: the my service A, which just says hello from A, running on profile A, and my service B, saying hello from B, running in profile B. Okay, there is a command line runner. Command line runners are small pieces of code which are executed. The run method is invoked when starting Spring Boot, and it just injects the service and not a specific implementation, but the interface. Okay, let's take a look. If we are just building it, and we are executing it. And what's happened is, it blows up, okay? Because if you activate no profile, there is no implementation for this interface. So activate profile A, it says hello from A. If you activate profile B, it says hello from B. Okay, great. So let's take a look what happens if we enable the AOT mode. So this is also active on the native image. We enable the profile A and it blows up. Yeah, great. We enable the profile B, and it blows up. Great. How to fix that? First, now we need to specify on build time which profile we build, because the profile says which beans are active. Okay? And I added So this is the snapshot documentation, but we released Spring Boot 3.1 yesterday, so it's now in the official documentation, and it tells you how to configure it. You configure the process AOT task essentially to activate profile A when building. So I'm building it again. Here you can see it's active, okay, in the build time. And now the beans which are active in that profile are always active. You can't switch them off, okay? Hello from A. If you activate profile B, you still get hello from A, okay? Because this profile is now baked into the code path. And if you started without profiles, it's still profile A. Now going to compile that stuff on native to show that the exact same code path is used for native. So all the AOT generated code is then used for native image. It behaves exactly the same. You can't switch that profile off anymore. Okay, B is still A. If you remove it completely, it's still A. You can't switch that stuff off because the bean arrangement at build time is captured in source code, which is now fixed. But you can change some configuration properties. So for example, you can change the logging level. Every property which does not affect the bean arrangement is still working. Okay, so now we've seen how that stuff works under the hood with a lot of source code generation and other tricks. There are two ways of building native executables. The first way is what I've shown, the native build tools. This is what Sébastien also used for his pet clinic. The native build tools, they started out at a collaboration between Spring and the GraalVM team. We have a great collaboration with the GraalVM team. We do weekly meetings and discussing stuff. It's really, really cool. And recently the Micronaut team has joined. Okay, so they're using that stuff too. You can compile your application and you can test your application. So the test thing which I shown earlier, it's possible with the native build tools. But it requires a local GraalVM compiler. Okay, so you need to install a GraalVM distribution on your machine. And what this thing does, if you type Gradle u native compile or maven-p native compile, you essentially get a native executable, and this executable is the same architecture like you build it on. Okay, if you build it on a Linux system for x64, you get an executable which you can only run on the Linux system. If you compile it on macOS, you can only run it on macOS. Okay, so there is no cross-compiling support. But all major operating systems are supported, even this thing here, macOS, Windows, and I'm delighted in GraalVM 23.0 there is improvements for the Windows users because you don't need to use the Visual Studio prompt or whatever the thing is, but you can just execute it and it finds the Visual Studio because it needs a C compiler. It finds Visual Studio automatically. The other thing is if you, for whatever reason, don't want to install GraalVM locally or you want to use container-based builds because they give you optimized containers, you can also use the build packs. And the build packs are container-based builds based on the open source build pack specification. It has compilation support, so there is no testing yet. It requires Docker, but no local GraalVM installation. You essentially give it your source code and then it does all the stuff and it pops out a Linux container image for x64, which is officially supported, but the ARM support is work in progress, which will bite you if you use, for example, M1 or M2 Apple machines, but Dashaun has done great work on it, so there is this tiny builder from Dashaun, which is essentially enabling building that stuff on ARM machines. Those are the two ways, and you can decide whatever fits best for you. Okay.
Okay, so let's share some data points. Just maybe an addition to what you said. Usually you want to maybe build a native image on your platform closer to the infrastructure where it will be deployed. So with the build pack support, if you are on x86, you can build it from either Windows, Mac, or Linux, and it will create a Linux image container that you can deploy on production potentially. But for more deep platform integration, maybe you want to build your native image on the CI/CD platform, when you know the technical architecture, usually Linux, but could be different CPU architecture later in the process. So you keep deploying a fat jar and you will create, you build the native image from source, or there is also a way to create a native executable from the fat jar if you want to do it later in the platform. So some data points. So in terms of startup time here, that's a Kotlin application, but we have basically the same result for Java as well. We try to measure the startup time in the cloud on small instances, because that's one thing to do measurement on your laptop. That's another thing to do that in the cloud on cheap cloud instance. So here, I push the limits to using very small instances, like a quarter of CPU, half of gigabyte of RAM. And you can see that the GVM is not really designed for that, and you see pretty long startup time. But you can see that the ahead of time optimization on the GVM, when you are running on small cloud instances, make quite a big difference on cloud, while on your laptop, maybe the difference may be smaller. And you can see that native, regardless of the size of your application, it starts instantly, even in super small cloud instances. So I think native really delivers in terms of startup time, including in production, including in very small application. So that allows you to scale to 0. So if you are using platform like Azure Container Apps, or Knative, which is a platform based on Kubernetes that allows to scale to 0 when there is no HTTP request incoming. Basically, you will configure your platform to scale depending on the workload, the HTTP request, and when there is no request, you pay nothing. So that's basically the serverless billing model for your application. Obviously, that depends also about the latency of your platform. So check on each platform how fast the platform is able to pop up a new container and serve requests, but that's offer interesting capabilities. In terms of performances, so you can see here that when you have very low resources, native is better, because basically it has a better resource utilization, so there will be more memory available for your heap, where the GVM infrastructure will take more memory and will produce lower performances. But when you have basically 2 CPU, 2 GB of RAM, the GVM begins to be better. And you can see that there is quite a big difference of performance between the community edition, open source version of GraalVM native image and the enterprise edition, which is closer to the performance level you have on the GVM. This is really for the throughput. For latency, they are close to the same on this kind of application. This was with Pet Clinic. And even with the community edition, when you don't have a lot of resources, community edition of GraalVM is better than the GVM if you have just one CPU and not that much memory. And it is per instance. So basically, the goal with native image, you will provision smaller instances, and you will have a platform that if you need more throughput, it will just provision more instances, more replicas, and that's it. It's just that the entry point, the minimal amount you have to pay, is smaller. In terms of memory consumption, so here I got the memory returned by Azure Container Apps after getting the first request of my simple web application. With the GVM, we have 170 megabytes of RSS memory used. You can see that ahead of time optimization allows to get reduced memory usage because there is less Spring infrastructure used. This is just lambdas creating beans, etc. No need to load the classes, less reflection, etc. So less infrastructure used. And native here provide a significant gain in terms of memory after startup. Obviously, the heap memory used when you process requests are the same, okay? You need to load the same object in memory, but the cost of the infrastructure is lower. So if you are splitting your application in a lot of small microservices, that reduces the tax you have to pay for each instance running, and so that may be interesting to get more memory for your application, for your heap. Container size, so that's not the most important metrics, because in practice, most of the cloud platforms implement caching of the images. So typically, you may see a difference the first time you are deploying a new version of the application. But after that, if you have a scale to 0 platform, this will be cached. So no real differences. But still interesting to see that with native, we have a smaller image because we are just using a more minimal operating system with just glibc, OpenSSL, and a few libraries. While on GVM side, we need more stuff. Also, we need also all the GVM. And there is also this option to use UPX compression, which is an option in Spring Boot and Buildpack support that allow to compress the executable using the very nice UPX algorithm. But in practice, I don't really recommend it because that will increase the memory consumption, because when the application is starting, when the container is starting, it will uncompress your executable. So this is super fast. You will see any impact on the startup time, but you will see more memory consumption. So in practice, maybe just keep the default. And UPX only if you need super, super small container images.
Cool. Let's talk about observability, because there are some caveats. So normally you have two ways of adding observability. The one is using JVM agents. So I attach a JVM agent. The agent does magic bytecode transformation, put in all the instrumentation probes inside your JDBC connectors and stuff like this, and then it starts reporting. Okay. And you can also use micrometer tracing, which is more explicit because you see it in your code. So the thing with JVM agents is that the stuff you're running in a native image is not a JVM anymore. Okay, it's a native image. It does not know the concept of bytecode. So the problem is the JVM agents are working on bytecode, so that stuff all falls in a heap. The good thing is some agents work, but you have to specify it when building the application. Okay, so then the agent kicks in while building the native image. It transforms then the classes, and then they get compiled to a native image. But your configuration is fixed. You can't switch it off. You can't change the backend. The other thing is using micrometer tracing. This was the other big feature in Spring Boot 3.0, the first class support in the whole portfolio project. It's all instrumented using micrometer tracing. And micrometer tracing is essentially SLF4J for tracing. And then it all gets exported based on the exporter you put at the end of the thing. So for example, you can put it in Zipkin and Jaeger and OpenTelemetry and whatever else you want. Actuator is working in a native image. So this is a screenshot from a curl request against the Prometheus endpoint. So you see all the metrics are there. You see process, uptime, system loads, how many JVM peaks, threads, and stuff like this. Okay, it's all working. And this tracing is also working. This is a screenshot from Wavefront. So this is using micrometer tracing and then the Wavefront exporter to show it in the Wavefront UI. And here you can see there is your span, your trace, then there are your service spans. So it's just working out of the box without any agent magic.
Yeah, so we plan to continue the close collaboration we have with the GraalVM team to support upcoming GraalVM improvement. We continue to collaborate closely to improve the scope of the GraalVM reachability metadata to support more open source libraries, to collaborate closely with the GraalVM team to improve performances and compatibility. And yeah, I think that's been a super nice collaboration that we plan to continue and push the boundaries of what is possible with Spring Boot and GraalVM. So yeah, thanks a lot.
Thank you very much.
Not sure we have time for questions. Maybe we have been
We have a little bit of time.
Okay,
have
so
like
if
5
we have
minutes. Any questions?
Yeah, is there some microphone?
The microphone is coming.
I see a...
Oh, sorry, the microphone went up there.
Sorry.
You're not forgotten.
So my question is regarding the profile feature.
Yeah.
Was this a conscious decision to kind of eliminate the possibility of changing the injection? I know this is not a good practice, and I haven't done this in a long time on production or production code, but it feels like you kind of killed the feature. Was this a limitation you found and you couldn't find a way to make it work, or was this like, is this here to stay and like this will never be allowed?
Yeah, I think this is a bit by design. AOT compilation, by design, you are going to fix more stuff at build time, and Spring Boot is originally super, super flexible. You can change everything because everything is computed at build time. So we can refine, and we plan to refine some behavior, like we have an incoming enhancement that will make sure that the profile enabled at runtime, when we have set one profile at build time, will be more consistent, and maybe throw error messages when you have inconsistency, or make sure you are really doing the right thing. We could potentially implement some kind of condition support with AOT, but that will impact the footprint, and I'm not really sure that's needed. What was missing until now is that it was not really documented how to specify profiles at build time, and now that's the case. We need to refine a bit that, but I'm not sure we will. I mean, in theory, we could implement something like a subset of condition will still be evaluated at runtime, etc. But this is a huge engineering effort, and I'm not sure. We maybe have other priorities. So we are listening user feedback, and we will see. But I think we will refine what we have. But there is by design reasons for doing that. And with native, you are already fixing a lot of things at build time. So with native, even if we do some stuff on Spring Boot side, yeah, you need to basically identify clearly what is included. You cut the rest. You are removing a lot of in infrastructure. So this is almost by design limitation.
All right, thanks. I hope you log a warning or something if you see the profile annotation somewhere, so people don't get confused if they.
Yeah, so we really plan to improve the consistency between build time and runtime profile. We have an open issue, and that we are currently working on that.
There in the front was a question.
Hello. Hello. You know, in really business applications, there are a lot of dependencies, and it's often hard to know if all the dependencies are compatible with native. Is there some analysis tools to just say and have a dashboard and on a report? Okay, maybe 10% of these dependencies are unknown or incompatible with native.
Yeah, good question. I think this is maybe something that should happen at GraalVM build tools level or reachability. I mean, it's not native, it's not Spring Boot specific. I think we have discussed a bit that at some point, but there is no real effort right now. But maybe, Ailina, maybe you have some.
Page, right? So maybe you can refer to that at the moment, but a tool would be helpful to have as well.
Yeah.
The website, other than reachability, there's also a page.
Yeah, so you have the page where you can basically, so if you go to the website, we can share later the link, you can check yourself. Yes, there is some underlying metadata, so the information is available in a structured way, in JSON files or whatever, on the GraalVM native image build site, so you can at least do manual stuff, but yeah, there is not yet this automated tool that we create reports, etc. But yeah, at least the data are here, and we have not yet built a tool that will automatically do it. Could be a good community project, require no interaction on boot side or GraalVM metadata. The data are here, so if somebody wants to play with that and create reports for GraalVM Maven and provide a native build tools pull request, I'm sure it will be integrated.
This stuff here is essentially generated out of a JSON file. Yeah. So you could download the JSON file, diff it against the dependencies in your application, and then spit out the stuff which is not in there. But it does not mean that if a library is not in there, it does not mean it does not run a native image. So it could be that it runs on native image, depending what the library is really doing under the hood. So it's doing crazy amounts of reflection and creating proxies everywhere. It's not going to work without configuration. But if you only use the non-reflection Java features or the not so dynamic stuff from Java, it just works out of the box.
Yeah. Okay, thank you.
Okay, maybe it's a stupid question. It's about Kotlin, and I know that Kotlin native and GraalVM are different paths, and if you use Kotlin with the Spring and try to compile the Spring native, you pass around the JVM compilation, well, the JVM path of the Spring. Is there any synergy, something to explore maybe? Because I feel that Kotlin native is the team is making a work and an effort, and this is another effort. Are there any communication synergies in order to I don't know?
So both are based on the LLVM compilation toolchain. So my point of view on that, I like Kotlin, I push a lot for Kotlin, but when it comes for running server-side workloads, I think the GVM ecosystem is impossible to avoid. And I mean, I try to use Kotlin native, I like Kotlin, but you quickly get a blocking point because you need to have...
You don't have enough libraries.
Yeah, you don't have multi-platform libraries that much. You need to use the CInterrupt tool where you need to spend 2 days to use the TNC library doing manualism mapping, etc. In practice, that does not fly. So my take on this is that for creating native executable with Kotlin for the server side, using Kotlin plus GraalVM is really the way to go. I share that with the Kotlin team, and yeah, I don't see Kotlin native getting a huge traction. So for the native side of things, I'm not sure Kotlin native will be super successful for server-side workload. GraalVM plus Kotlin, especially with a good Spring Boot support, is just better, and you can use your GVM ecosystem. So.
Okay, thanks.
Thank you for your hard work and for the presentation. I have one question regarding the plot that you had the request per second. There was 2 plots, and one was for the GVM and native community and enterprise. Yeah, that's not the
This one.
This one.
Yeah.
I have a question. You see that the last one, when the memory goes, when we have enough memory, why the GVM performs better? Isn't the native should go, let's say, better and better than the GVM? That means that we need to optimize, let's say, to have many small instances to have for the same resources we have the maximum performance, isn't it?
So here the performance I took is with a fully warm-up GVM. And I mean, it's well known that the fully warm-up GVM is super fast and hard to beat because there is dynamic optimization to the workload, etc. On native side, I on purpose did not use the PGO optimization. So there is this mode only available with GraalVM Enterprise Edition, where you can basically provide some sample workloads to make your GraalVM Enterprise Edition application even faster by learning from the real workloads. And here, I think we could be same or faster than the GVM. But that's painful because you need to have some sample workloads. So basically, you need to deploy your GVM application on the production, get some sample loads, create the PGO, deploy it. It's honestly quite an involvement that requires deep platform integration. So here, what I used for this performance measurement is just a native executable that has no understanding of what kind of workloads it will receive. And GraalVM Native Image does a pretty good job to optimize stuff, but it can't be, or I mean, I think GraalVM Enterprise Edition, especially with the upcoming performance improvement, it's getting closer to the GVM, but I think it's reasonable that the GVM is faster when basically you create a native executable with no ID of the incoming request because, yeah, the GVM can optimize specifically the controller code path that will be used and dynamically adapt. So a warm-up GVM is pretty hard to beat, even if you use Rust code or I did some benchmark. A warm-up GVM is really super fast and really hard to beat.
Yeah, it's a marvelous piece of technology.
Yeah, but the PGO, right?
Yeah,
So
yeah. And so on purpose. Yeah.
Yeah, that's interesting that now native application, like let's say maybe it needs more optimizing, but now it needs to catch up with GVM. That's really awesome. Like in early 2000, it was only talks about how slow it is. And I have also a couple of questions like regarding debugging. So debugging not when it's Java code, but it's when it goes to the native. And another one that now you have reflectionless dependency injection. Is it possible that it will be a separate library which we can attach in a Gradle like with annotation processor, just like in Android there is a Dagger 2 and it's just removes the reflection because it's fights with performance.
You can already do that. I mean, the Spring ahead of time optimization, this is a specific Maven and Gradle plugin that we automatically invoke when we detect the native build tools. But if you go to see the documentation that Moritz, so it's available in the Spring Boot 3.1 documentation or the samples there is in github.com/sdeleuze/spring AOT, whatever. You will see that you can enable only the plugin for AOT without native involved, and you just enable the AOT mode, and you get this reflectionless code path used, no native involved. So I'm not sure if that's a question, but yeah. AOT optimization are already available. Just it was a bit hidden because we have really built AOT optimization with native in mind. We plan to do more work to leverage more transformation at build time to go further, but it's not clear what will be the scope yet. So we were not sure how much we document that, and recently we said, okay, let's at least document it what we have. It's possible to define profile at build time, so we can go pretty far. And on production, we have seen during the keynote, 7 seconds for container startup without the GVM AOT optimization, 5 with one on a 1 CPU machine. That's already a pretty good improvement, less memory consumption. So if you are ready to fix a bit the environment variables, etc., during the build time, that's a free lunch. So,
I think we have to cut it here.
I just wanted to add that if I can run 2 pods with the same memory footprint, with which of 1 copy of GraalVM, which architecture is handling more requests in the hand. I mean, if I can, with the same memory footprint, scale to 2 native pod with the same memory footprint of 1 GraalVM pod.
Yeah,
exactly.
Exactly. So that's a very good point. The way you scale with native is you will provision smaller instances, and if you need more power, you will basically add 2 native instances instead of potentially 1. So for CPU, that does not change that much, but for the memory consumption, you are able to scale in a more fine-grained way with native, and that's indeed something interesting. Thanks a lot. Bye-bye.
Thank you very much.